Now we're going to look at some circuit variables, namely current I, voltage V, and power P. First of all, current is the net flow of charge per unit of time. Express this in terms of derivatives. The current is the first derivative of the charge with respect to t, or time. And this is how we define current. And its units, as you recall, is amperes, which is really coulombs per second. So when you're looking at one point in a particular circuit, that's what we call current, in which we count the number of electrons passing through that point in a given amount of time. Again, we have Q as charge, which is given units of coulomb. T is time, given as seconds. And the current direction is the direction that is a positive charge that would flow through an element. Then we have voltage, and from our water analogy discussed earlier, this is the change in energy from one point to another. And we can think of voltage as the amount of charge or amount of energy required to move a coulomb of charge, because it takes energy to move charges from one point in a circuit to another point. So voltage is a relative measure and is measured across an element, whereas current is measured through an element. An element, what I mean, is like a resistor, capacitor, or inductor. Now the definition of voltage, as I said before, is the amount of energy required to move a charge. In this case, we can express it as a derivative. Voltage is equal to dW dQ, where W is in joules and Q is in coulombs. So voltage is joules per coulomb. That's the units. So the V is a measure of voltage, which is the unit of volts. W again is the energy, and Q is the charge. Our final circuit variable is power, and it's related from the previous two variables. Power is the rate of energy transfer. So it's can be expressed as a derivative here, the amount of energy that you give in terms per unit time. The units is in power. W is in joules per second, and T is the time. So power is joules per second. When we analyze circuits, the power is absorbed from the circuit by an element or delivered to the circuit by an element. So a voltage source will deliver power and a resistor will absorb power. Because energy is conserved for the circuit, all the energy is delivered to the circuit is absorbed by other elements in the circuit. Now the relationship between power and current and voltage is given by this formula, P equals IV. A nice mnemonic that I use is poison ivy. Now, using Ohm's law, we can relate the power in terms of resistance with the resistant element. So for a resistor, we know that Ohm's law, V is equal to IR. Substituting for V in terms of IR, we have I squared R. And substituting I in terms of V over R, we have V squared over R. So for a resistor, this is the amount of energy that gets dissipated or absorbed by this, let's say when it's connected to a voltage power supply. So let's go through an example involving units, and we'll start off with this cathode ray tube shown here, diagram. And what we have is a cathode ray tube where the cathode, which is denoted as the minus potential, and the anode denoted as the positive potential. We have a battery source here to accelerate 10 to the 14th electrons per second through the cathode ray tube, and we're given a voltage source of 50 kilovolts. We'll put the longer line associated with this DC source is a plus, and the shorter line is denoted as a minus. So once again here we have this 50 kilovolt voltage source accelerating this electrons of 10 to the 14th electrons per second. Alright, so what we want to find is the power of the electron beam going through this cathode ray tube. So since the current is the rate of charge flow, we can find the net current by multiplying the charge. So here's our current multiplied by our charge Q of an electron, subscripted with a cap E for electron, and we're going to multiply by the rate of current flow. We'll just call d n e dt, but we're given that as 10 to the 14th electrons per second. We note that the charge has a value in terms of Coulomb to be 1.6 times 10 to the minus 19th coulombs. Okay, and then the number of electrons per second is 10 to the 14th per second. So this is 1.6 times 10 to the minus 19th coulomb per electron, basically, and this is 10 to the 14th electrons per second. That's our NE in here. Okay, so here's our derivative for that expression. Evaluating this expression yields 1.6 times 10 to the minus 5th amps. Now the power we discussed earlier is P equal IV. Well, we're given the voltage of 50 kilovolts. We just found our current, so we just multiply those two variables. So that's basically 1.6 times 10 to the minus 5th amps multiplied by 50 kilovolts, which is times 10 to the 3rd volts, which yields 0.8 watts. And that's our answer for our power given here. So let me highlight those answers.